Hello, good morning, everybody. So the first is thank you also, Jasmine from Jordas, to organize the webinar and this important around this important topic on exposure to nanomaterials and nanoparticles. So I'm Carlos Fito. I'm the head of the Health, Safety, and Environmental Monitoring Technologies from Etienne Research Institute. So today in this workshop we have also my colleague Helena from Etienne, also for our department. Our idea during this first hour in the workshop is to try to show you the different methodologies that we can use in workplace to detect and measure nanoparticles. And also Elena will also explain and describe the new NanoExplore device that the consortium have developed under the project to measure this kind of materials. So the first part of the workshop will be about a brief explanation of the different procedures to monitor the exposure in workplaces and when we are working with these special materials, so with the engineering nanomaterials. So at the end, from years, we have been working on projects and measuring and taking ID of the different levels of exposure in workplaces. There are a number of methodologies, and also there are different devices that we can use in workplaces to measure and detect number concentration or mass. But in the project, we have developed different technological solutions to come up with a device that can be used by occupational health and safety advisor, for example, or also it could be used by the public authorities or people that is working in environmental monitoring. So I hope that you have today a big picture of the different developments that we have in our project. Of course, you can also contact myself or Elena and other colleagues from the project if you want more information or details on the use of this kind of devices. So the first part is just an overall view of this specific topic about nano exposure and nanomaterials. So at the end, we are going to focus more the project on this kind of materials. So you know that a few weeks ago, there was also a publication from the Commission with a new definition of the nanomaterials. But normally we understand these kind of materials as particles that are in the range between 1 nanometer and 100 nanometer, but it's very difficult to find this kind of specific materials involved in the occupational workplaces and also in the environment, considering this kind of size range between 1 nanometer and 100. At the end, these kind of materials have different kind of processes like aggregation, agglomeration. So normally we find bigger agglomerates of materials, but individually we can observe and we can detect this kind of particles. So as you know, at the end, these kind of materials are here from years. So some of them can be generated in the environment and the different kind of dynamic processes in the endospheres. But here in the NanoExplore project, we are much interested in the materials that we can find in the industrial settings, in the industrial workplaces, but also in around the cities, for example. So it's something like more environmental related engineering nanomaterials. So in terms of particles and the chemistry of the particles, is very different. So it's a kind of two different worlds. So we have one kind of material, so that are complex, normally are based on the release of the products that the companies are using in the industrial scale. And then we have in urban area, for example, materials that are coming from different kind of sources. So for one side, we have sources like the traffic, where we have the vehicle exhaust, for example, or we have some methods in the nanometer range from the brake and tire abrasion, Also, we have some materials that are coming by dynamic atmosphere from the industrial sources. Then also we have dust coming from different areas. So there's a big mixture of different kind of materials. But in common is that they have this nanometer range. And of course, we have to consider the common particulate matter in terms of PM 2.5 and PM10. And here also we are very interested in the ultra fine size range, so normally below 1 micron. So in the project, we have been working for 3 years or trying to come up with new data on the potential exposure levels in both this kind of industrial facilities or sources and also the environment. Most in the urban area, considering areas like the traffic, a big traffic road area, for example. But also we are working now in compiling information from different areas like parking or closed areas. So at the end, we will come up with different kind of data that could be used to, for example, by public authorities or decision makers on defining potential threshold levels of exposure in the future. So at the end, when we are working in the different areas or compartments, we need to consider the potential type of materials that we expect in this area. For example, in the indoor areas, talking also always about companies, and normally we have processes like the synthesis or formulation of different kind of materials. So then we can find in the air like primary particles or pristine particles when you open, for example, a bag with the materials, or when you are or compiling the particles into a bag, doing, for example, the packing of the materials. Also, we can find aggregates and agglomerates. That's also a common process. Then also you know that there are a lot of activities where we introduce materials into another kind of matrix, like for example a polymer, and we can also make some mechanical activities in the polymer. So at the end, we will find fragments of the polymers with a sub-micron size or below 1 micron. So that's also common. And then also we have sometimes these polymer coated particles. So at the end, we will have different kind of materials that we can find. In terms of the urban area, at the end also we can find primary particles, mostly are methods that comes from different kind of sources, like for example the trains, and then also we have common agglomerates and aggregates. That's common because at the end in the environment we have different dynamic processes, and in the real outdoor area like the air or surface water and soil, also it's possible to find particles. We can find normally material that are in the nano range, but not all the particles are for industrial sources. So some of them are naturally generated particles. We can find also in the water. Now is very important the terms of nano and microplastics. So we can find materials in terms, for example, of sub-micron size polymers and nanoplastic that are in the water, and also in soils. In different projects, we have been trying to analyze the potential concentration of the materials in soil. So that's very important. So in terms of what we expect in industrial facilities, at the end, normally when we are working at the end making some exposure campaigns, we used to identify like 3-4 main sources of emissions. So we have these primary sources that normally are related with synthesis process of the nanomaterials, like the flame spraying or the milling. That's more mechanical. Also the CBD, for example. So at the end, we can find different kind of engineering nanomaterials in the environment. Then also we have secondary sources of aerosols. For example, when you are just making a manual packing of the materials. So sometimes we can find this kind of information in in the workplace. Then also we have this harvesting or the melt blending of the materials, so that's also very, very common. Then also we have a third kind of source of release of this kind of materials, like for example spraying, the rushing, injection molding. So the big difference is in this kind of tertiary sources that we have a bigger amount of materials, some of them engineering nanoparticles. And then also in the primary source, normally we find the pristine particles. And there are another kind of source domain or source of release of materials, like the grinding or the abrasion of different kind of structures. So at the end, there are like these 3-4 main sources of release. These kind of sources of release are normally used as a common terminology, for example, when we are preparing exposure scenarios, or for example, when we are trying to estimate exposure using models in different kind of processes. Then you have here some specifications of the expected materials, considering this kind of emission sources. For example, in the first case, when you are producing materials, so we expect normally single particles, and the release potential is likely, so we are expecting a release. Then in the case of the second subdomain, when you are handling material, for example, then we can expect single particles, but also we can expect aggregates and agglomerates, and of course some embedded particles with the polymers. So when this is very important in terms of the exposure, because it's not the same be exposed to single particles, in the nanometer range, or be exposed to these larger particles. So in terms of toxicology and potential exposure, it could be different. Then also we have the third domain with the mechanical processes and also the spraying processes, where we have a big number of materials, thousands or also millions of materials, but only part of them are related with the nano or the engineering nanomaterials. We can have also single particles, but normally we have a mixture between the drops of the liquid plus different kind of particles. And then we have the mechanical abrasion, for example, drilling, grinding, where we have millions of materials, and much of them are embedded in the matrix. So that's important when we are trying to come up with an exposure scenario. The second question is about the threshold levels that we have when we are developing or we are making risk assessment with nanomaterials. So at the end, in toxicology, we have different limits of exposure. For example, that we have to include under the risk registration, or where we are doing an occupational health and safety report. But here, in terms of exposure levels when dealing with nanomaterial is different, because there are a big lack of data considering the chronic exposure to nanomaterials. So we don't have these common derived no exposure effect levels for nanomaterials, but there are some proposals for this kind of materials in terms of occupational exposure levels by different international organizations. Today we have like 4 main occupational exposure levels. We normally say recommended or proposed occupational exposure levels. For example, we can say that for methyl and methyl oxides, for example, we can use these numbers, for example, silver or iron oxide or therium oxide. We use this 20,000 particles per centimeter cubic if we are measuring in number concentration. Also, there are other kind of materials that we can measure up to 40,000 particles per centimeter cubic. But when we are working with fibers or high spectral materials, we are counting in fibers. So we need to identify first, when we are doing this risk assessment, the type of occupational exposure level that we can use to compare between these numbers and the real concentration that we measure in the environment. So last week we were participating in the Nano Week 2022 in Cyprus, and then the course meeting. That the course is a kind of international group between researchers from Europe, and researchers from the United States, and one of the sessions were about this kind of occupational exposure levels. So there are now some new proposals by the researchers that are very interesting. So in one of our deliverables in the project, we are going to include the last information on the proposed recommended exposure levels that includes several differences between this table and the news that we have. So it's very important to know that there are a lot of work behind this level, and there are organizations like NIOS, for example, in the US, that are working on this kind of proposal levels. And also in terms of Europe, under the nanosafety cluster project, there are a lot of initiatives to try to come up with different values to make easier the risk assessment when we are doing an exposure campaign in the companies. The third question is about how we can make the analysis of the exposure. So, as you know, normally as occupational health and safety advisor, we need to measure the potential concentration. Normally, we use the mass concentration for bulk chemicals. But when we are dealing with nanomaterials, normally we use another metrics. So we use the number concentration. So the OECD in 2015 and also in 2017 published some harmonized protocols to measure. It's a tier protocol, tier 1, 2, and 3, to measure the potential concentration of nanomaterials in workplaces. And also there are different proposals from NIOS, like the NEAT methodology, that is more or less the same. At the end, always we have to start with a questionnaire, as you can see in the figure, just to know the potential hotspots or the potential critical areas of release. If we observe that there is a potential of release, we can measure with simple instruments, for example, number concentration with particle counters. And then if we have a big increase of the materials in terms of number concentration, compared with the background concentration where there are no activity, for example, or between the near field, that is the area close to the process, and the near and the far field, that is the area that is far from the process, up to 6-7 meters, we can understand that there is a potential release, and we can go with a tier 3 analysis that is based in more robust devices like the particle sizes, like the FMPS or SMPS or the APS, that are all instruments that are based on number and particle size distribution, and is normally completed or coupled with electron microscopy analysis. So at the end, we will have a lot of information to decide if there is or not a potential exposure in workplaces. As I know, as I mentioned previously, we can use questionnaires. So this is one of the questionnaires that we are using with clients and in the framework of different projects. So it's just a compilation of information on the activity, the process. So there is a concept that say determinant of exposure. So determinant of exposure is about which are the main characteristics of the process and how you use the material that determine the potential release. So we try to analyze the amount of material, the room where we are doing the process, the level of containment is not the same using a clean room or using a big laboratory, also the exposure duration, and of course the effectiveness of the different controls that we have. We have ventilation, we can have containment and filtration, but also we can have protection, personal protection equipment. That's the last one, the last barrier that we can use. After compiling this information, we can analyze all the data. And then if we understand that there is a potential release, we can visit the company. We normally use particle counters, simple CPCs, for example. There are some of them based on different technology, but normally we use these particle counters based on the condensation of materials. And normally we measure around the particle breathing zone. That's more or less 30 30 centimeters from the mouth. We use normally a tube if we are not allowed to go into the process, just to catch this information from the process. The first activity that we need to complete is to plan at the end the activity. We need to understand the process of the client, or the process of the company, or the area where we are going to measure. Then after planning, we can have a meeting with the colleagues in the company, then define the proper set of devices that we can use according with the type of materials, the potential site distribution of the materials, and then we go for sampling. And during the sampling, normally we measure, for example, from 1 hour, the background levels. Background levels could be like the levels of materials when the activity is closed, so there are no people working in the labs, or there are no people working in the company, or before the processes. Sometimes, for example, we measure 1 hour or 2 hours before the process start, just to have an idea of the potential levels of exposure in the background noise. Then during the activity, we measure with this kind of devices. In this case, we can start with a simple device like the particle counters. There are also other type of devices that I want to tell you in a couple of minutes. That is, for example, the Partector, or this mini, or nanotracer, that are based in other technologies, but the same. We can measure particle number concentration second by second. So there is a lot of information that we can compile from the companies. At the end, the more relevant thing is to try to make a good planning of the campaign, sampling in the particle breathing zone, so close to the mouth, because we are trying to analyze the potential inhalation of the materials in the workplaces. This kind of instrumentation only tells you about the potential concentration, but not the chemistry of the material. So normally we prefer to combine in this tier 2 analysis the particle number concentration, but also using filtration sampling in pumps, for example, just to go with this sampling to the microscopy, and then analyze using SEM or TEM the chemistry of the materials. Otherwise, we know the number, but we don't know exactly if we are, for example, we have like 10% of silver and 90% of other kind of materials, because we are, for example, developing or making a synthesis of silver particle, or we are producing a polymer where we are using silver to reinforce the polymer. So we need to know the potential expected concentration. And at the end, for a big process where there is a big release of materials, or if we are very interested in understand the levels of exposure, the site distribution of the materials in the area where we are developing the processes, we can use a big number of instrumentation, complex instrumentation. For example, the scanning, the SMPS, that tells you about the particle size distribution of the materials, the aerodynamic particle sizer, for example, also to measure inhalable and respirable particles in the area. We can use also impactors to collect in filters materials under different size range, and then go to the microscopy and determine the chemistry of the materials. Here you have just an example of a big number of instruments that we include in some of the campaigns. In this case, for example, for graphene and graphene oxide production facilities. For the filtration or for the sampling, we normally use polycarbonate filters. So these polycarbonate filters are been using for years. Also, we can use cascade impactors just to distribute in filters by size distribution. That's also very, very important. Or also we can use cyclones, for example, in the inhalation or respirable size range. So that also tells you more details on the potential size distribution of the materials and the chemistry, considering the different sizes of the process. So that's very relevant. And the big issue that we have when we are working with nanomaterials is the price of this kind of instrumentation. If we use condensation particle counter, for example, we can have one for 7,000, 10,000, depends on the number of devices that you want to buy, all the things, and the negotiation. But also it's very important to have safe distribution. So we can use a nanoscan, for example, that is more or less something like 25,000. But if we want to measure more details, we can use an FMPS that it costs like 80,000. And there are more instruments around 100,000 euros. For example, the new ones that tell you about mass distribution in size. There are also low-cost instrumentation like the optical particles counting, like the OPCs, that it costs like 400, 300, but at the end, the robustness and the reliability is different. It's not comparable to the bigger instruments or costly instruments, but always helps you to have an understanding of the potential distribution of the materials. But of course, if you are interested in the size range, considering nano, you have to go to particle counters. You can also use cyclones to decrease the size that you are measuring, or scans like the nanoscan or the SMPS. So normally it's what we normally include in the sampling campaigns. You have here a big picture with different kind of instrumentation that we have in the laboratories. In the first part, you can see the nanoscan, the optical particle sizers, the dust tracks, nano tracers, nano watcher. So all this information, all these instruments are for particle counting, and some of them, the first two, are for size distribution, but they are not very costly instrumentation. For laboratory activities, we can go to different kind of instrumentation like the FMPS or SMPS. They are devices with a powerful resolution, but of course are costly. And then we have the sampling, so the samplers, common samplers for gravimetric analysis or impactors. Also we have the Decati impactor that costs like 70,000, but at the end, the information is quite different from the one you will get using polycarbonate filters. But for a campaign, is more than enough to have particle number concentration, some information on the distribution, for example, using cascade impactors, and then the traditional filters, so for the chemistry analysis. So at the end, we will have some details. So normally we use this multi-instrument approach, and we have to make this tier approach. Tier 1 is the simple, using the questionnaire. Tier 2 is counting and normally coupled with filtration elements. And then tier 3 is like the last one that is using this size distribution instrumentation. So you have some scheme that we have in Hygiene to measure. This is our plan for developing polymers. And you can see that we are using different kind of instrumentation to detect and measure the particle number concentration, the mass, and the size distribution using this different kind of instrumentation. All this information have to be compiled, and then you can just make a plot analysis of the background and the level of exposure. You have here a summary of the different steps for the different analysis that we can perform. I normally recommend the tier 2 analysis for a first occupational health and safety analysis of the processes. And then if you have or you identify a big release of materials, not in peaks, but it's very continuous in time. So normally it's recommended to go for a tier 3 analysis. So trying to come up with more details on the potential concentration of the materials and what materials are you at the end exposed to. So that's very, very important. That's a common representation of this kind of measurements. Here you can see a plot when you have a start and the middle part of the processes. When we start, we can say that is the background. So background is when before the processes take part, 40 minutes or 1 hour before the processes or the process start. You can see a red line around 5,000 particles per centimeter cubic. Is not too much. Normally, when you are measuring something like 2, 3, 4,000, at the end is like the background, the normal background in a laboratory, because these kind of instruments can detect 1, 2 particles. So at the end, you always have something in the environment. In this room or in your home, in your house, you will have something like 1, 2, 3,000 particles. And then you can see that when the process starts, you can see a big increase in the slope of the plot. You can see big peaks up to 50,000 particles per centimeter cubic. That means that we have a big release during the processes. So normally this is the kind of plots that we implement in the analysis. So that's for example, for nanoclays. So we are reinforcing nanoclays with silver particles, in this case silver nanoparticles. So we are loading, as you can see in the picture, one of my colleagues, they are loading, pouring the particles in the hopper of the extruder, and we can have this kind of increasing release of materials. Here, there is another example of a textile process. So we are drying textile after including a coating, a nano-based coating in the textile, just to protect the fabrics. So you can see also different kind of peaks. So these peaks are very common when you are working with nanomaterials. So normally you have a big increase and then a decrease of the materials. So you can see that we have NF is near field and FF is far field. So in the far field, we have a low number of materials. So that's like the background levels. And then we have like the near field, that's something like 0.5 meters from the source, and when the technicians are applying the nano coating for UV protection, for example, we can see an increase from the levels in the background. So there is a release of material. The thing is that we need to know if this increase is enough to consider that we have a risk in terms of risk analysis of the product. So normally we consider that there is a potential realistic release of materials when we have three times the levels of the concentration in the background. So that normally means that we have a potential release. Also in the OECD, they include that if we have 3 times the levels of exposure, considering the concentration that we have in the background, but considering the standard deviation, also there is an increase. Today, normally we use more the threshold levels, like the recommended exposure levels, because normally in the companies you have a lot of processes. Some of them are active, some of them not. So you have a big mixture in the background level. So there is a big difficulties to differentiate between the background and the activity. So we prefer to use also the recommended exposure levels, just to have an understanding of where we are. The last part is just how we can interpret all this information. So normally we use the term exposure scenario. So an exposure scenario is the critical concept that we need to know when we are speaking about risk regulation and risk analysis. So the exposure scenario is a compilation of information on how we use the material, which are the amount that we are using, which are the risk management measures we are implementing. So considering this data, these determinants, we can say this is my exposure scenario using 10 milligrams of materials, using ventilation and filtration, using mass respirator, for example. So in this condition, I have this exposure, for example, 1,000 or 10,000 particles per centimeter cubic. Another process could be different, so different amounts of materials, different processes, different kind of risk management measure. That's another scenario. So that's very important to classify the information and make a good analysis of the processes. So you have here some examples of common exposure scenarios in workplaces. So we have the production of multi-wallet carbon nanotube, or we have the production of aluminum oxide, for example. In green is where there is a big release of materials. So the ratio between the background levels and the measurements is not higher than three times. As you can see in other areas, like for example, the packing of the aluminum oxide in red is like 9 times the background levels. Then we have in the harvesting of the carbon nanotube, we have like 10 times the background levels. So there is a big release of material. Also in the picture, you can see different metrics. You can see number, you can see mass in the center, and you can see surface area. Surface area is also important for nanomaterials because surface area is also related with the reactivity of the product. But you can see that there are big numbers in terms of number concentration, like 30,000. But in terms of mass, it's very low. It's not too much. That's also common. It's because the nanomaterials are very small, so there is no big mass of material normally in the micron range, or even in the nano range in some parts of the measurements. So now I also give the floor to Elena for the second part.
I would like to introduce myself. My name is Helene Prima. I am a project manager in the area of health, security, and environmental monitoring. And I would like to talk. This part of my talk is about the prototype of device that has been developed in the framework of NanoExplore. This was the first part. The second part, I will describe the setup, and the third part, I will tell you the success case we have validate and implemented this technology developed in the framework of NanoExplore. Okay, my objective of this wireless sensor prototype is provide instruction to operate the NanoExplore monitoring device. The expected outcomes is a comparable and interoperable register containing measurement data on the concentration of nanomaterials in different scenarios. The NanoExplore device is, as I said before, is a wireless sensor prototype. That means that can work without any Wi-Fi connection, has the self data in order to upload all of the data to the cloud, and also can save the data locally. Also have the utility, this field utility. This instrument is monitoring the nanomaterials and ultra-fine particles from 10 nanometers to 10 micrometers, and it's practical for field measurements. It's portable, autonomous, and have a screen light. Also it's useful for indoor areas and also for outdoor environments. The accuracy is have a good compromise, is a good resolution, and it's versatile with the technology that is available at that moment. Also, the data is easy reading and interpretation of the results for a first approach to exposure assessment. That means that not expert person can manipulate and can take the data of this device. And it's very useful to let the device in for example, in an industry, and the self worker of this industry can also validate and switch on and switch off the device. The particular matter is this device measurements particulates that are normally with different radius, and the nanomaterials that can penetrate when we are low of 1 micrometer, that is the nanofraction. These very small nanomaterials can penetrate respiratory and circulatory systems. That means the lungs, heart, brain, and causing up to 4.2 million premature deaths in the worldwide. each year these issues such as cancer, health, and land stage. For that is important that this offer a robust technology to disperse these nanomaterials in order to make the consecutive studies of toxicology. Normally, the setups that are in the same range of detection that this NanoExplorer device cost that more than 12,000 euros and are very heavy. And more of them are thinking to laboratories and are not remote operation. For this proposal, we think that this device is very competitive with the technology that is in the moment. For that, NanoExplorer takes advantage of a new technology. Has two detectors. One is a particle counter, specifically designed to measure and monitor in real time the concentration level of airborne nanoparticles in either industrial or urban areas. As I did before, the main features are portability, plug and play operation, a fast response time, low than 1 second. This will be a filtering system for direct particle analysis in 10 grains, and it has an autonomy of 24 hours. This destructive filtering is the device has some holes that we put a filter that can have a separated pump to absorb air in order to capture the nanomaterials that are in the atmosphere and deposited in these filters. Then this filter we can make microscopy analysis, scanning microscopy or transmission microscopy in order to detect what are the morphology, what are the size and the crystallinity of the nanomaterials to evaluate and make a good risk assessment of this process of this industry. Other important specification of the wireless sensor is the real time, has a high frequency continuous measurements, and can make a long-term monitoring and air quality studies. That is very important in order to be a device that is versatile, can work inside or also outside, and can perform can perform a good analysis of the exposure for a worker, for example, and also the environmental assessment or evaluation for outside of the industry or in the urban areas in order to measure the concentration of nanomaterials that came from the intense urban traffic of cars or so. Have smart operation software for remote configuration, standalone portable device. Its battery, the battery is a lithium-ion recargable for each hour around time. Can also will be add other atmospheric variables like temperature, humidity, or pressure. Also, its ability to collect filters, as I said before, in order to make later the analysis of microscopy, and provide user configuration and scheduling of main samples operation conditions. And everything is integrated in a whole element into a weather protection and portable structure, like a budget is very comfortable to carry this device. Okay, as I said before, this regarding the capacity of detect nanomaterials, the NanoExplorer device has two different detectors. One is the detector from the ultrafine nanomaterials, which has the following characteristic. The is capable to measure number concentration, mass concentration, lung deposit surface area, LDSA. That is an important parameter to analyze and to know what are the toxicology of these materials, have a numerical concentration, an average particle size, a total surface area, an inlet flow of 0.5 liters per minute, and we can program alerts for high concentrations. That means when the concentration of these nanomaterials is higher than a certain concentration, can be an alarm that can give send an alarm by email or by a message. I also have an internal micro data storage, and we can have a space for terabytes. Okay, the second detector is an optical particle counter. We can measure particles from about 1 micra, 2.5, and 10 micras. The first detector, I forgot before to say, go for a range of nanomaterial size from 10 nanometers to 1,000 nanometers. Then the optical particle counter, the second detector, or the more higher size for the nanomaterials, and have also is compatible and can measurement below 1 micrometers from 300 nanometers to 14 micrometers. But normally we use the detector to measure PMI1, PMI 2.5, and PMI 10. That is the normative and standard values that are measured in order to know what are the concentration for this free size. And normally it's a European normative. This is free size of the materials that are ranged in the respirable, thoracic, and inhalable fraction. Okay. It is possible also to have 24 size beams. We can also make studies and reprogramming. There is no problem. The total flow rate is 1.2, so a separated pump. The maximal particle counter is 10,000. That means that in a very heavy, dense with a high density of materials, could be have a problem with this maximum particle counter. But we have used this device in a busy industries with a concentration in a high density atmospheres, and has worked properly. It is and everything is pre-calibrated before we put in the market. Okay, and regarding the filter, regarding the part of the filter to gather nanomaterials that are in the air, we have a 10 grid. It's a grid. It's a metallic grid that can gather nanomaterials that are in the air. Is compatible with TEM experiments and with SEM as well. This equipment is capable of recording the flow rate, length of the samples, total volume to support an adequate characterization of the chemical natural nanomaterials. Has a flow rate up to 10 liters per minute. The maximum flow rate needed is 9 liters per minute. And the user will be able to set which flow rate it is necessary for his experiments. Other properties of this NanoExploreR device is geolocalized with GPS, and that is important because when it is working with wireless, it is possible to upload direct to the cloud the measurements, and also in the application that later will be explained. I can also know where it is in this point measurements. Okay, there is an option to measure background first, and then to measure a sampling mode. Also, as I said before, the samples can be collected at different flow rates. And this equipment is capable of recording a lot of nanomaterials because they have a pump that we can also later analyze to perform microscopy. It is compatible from outdoor indoor equipment. You can see in this picture here, in the picture above, it is the indoor device, and the picture below is the outdoor device, which has more autonomy than the outdoor, because we can charge the batteries with the solar cell. And the battery power is autonomous about 5-8 hours. Also, it's also important for the outdoor characteristic, the outdoor applications, is the temperature range. This equipment has been tested with a temperature range that go for -10 degrees to 40 degrees. Okay. Also, this equipment has installed a software that allows the user to monitoring in remote with application, a well-known application like TeamViewer. We have also a remote and local access to information of the levels of particles in the air or nano, and also the ultrascience measurements by the station. We can visualize the measurements in real time, also in remote option. And as I said before, have the possibility to send the data into a web server via Wi-Fi or data of free 4G data. Regarding the screen of the NanoExplorer, the NanoExplorer has a touch-sensitive LCD display. This function include the start, stop, and length of measurements, and the parameters included flow rate, the temperature, and the localization as well of the area that we are putting. And the data that we obtain, we can export the data in the very known format: PDF, Word, Excel, XML, CSV, etc. The application of this equipment is we can use as filter testing, indoor air quality for particles and nanoparticles, workplace studies, particles and nanoparticles, outdoor environmental monitoring, particles and nanoparticles, industrial measurements. We later on I will show some implementation and case study that we have made in industrial areas and as well in a train station. It is also we can use to basic aerosol research because they have a very high size range. We can also use to emission monitor and control and other aerosol related research topics. Then in this third part of my talk, I will talk about the example, the implementation of this device in the real industry. We have the ITENE team has been performed exposure campaigns using this device in different areas of Italy and Spain. And in this work, we have a characterization of the exposure in the workstation, how many we have measured, which are the concentration where the exposure workers breathe. ITENE will conduct these exposure measurements campaigns, and also during in the area in the far field and also in the particle breath zone. And the methodology that we have used is having explained by my colleague Carlos before, and is the methodology used the common method, the standard methodology, which is a nanoparticle emission assessment technique developed by NISO for identify source and release of engineered nanoparticles. In this regard, we will employ established practices for conducting exposure assessment, including multiple instruments suited for the detection of both nano and micro-sized particles, together with these 4 NanoExplorer wireless sensor units. Okay. we have validate our device in a paint industry, locality in Italy. In this industry, we have detect the following exposure scenarios: the power transfer, a mixer to perform the mixing of the product that they are using, and also the use of different nanomaterials in this chain production industry, the titanium dioxide, and also the oxide, iron oxide, and amorphous silica, and also some nanomaterials composed by organic volatile components. Okay. During the measurement, we have performed the different measurements. That is the time schedule that we have done, and also the device that we have used in NanoExploreR Workshop. These examples of how we can detect with our detector, we can see here that is measurement for the second detector, the detector that measures the particles with higher sizes, the PM1, PM2.5, PM3, and this is the outcome that comes directly for the data that it is shaped into the device. We can see here that is where the concentration is higher, mean a different process of transfer the power from one side to the other side, and it's correlated with this process. And we see that this background is higher, more than 3 times higher than the background. That means that has a really a risk. The risk is higher. As my colleague Carlos explained, we can evaluate that the risk is higher when the concentration of the nanomaterials during the production is more than 3 times above the background measurements. Also, we have measured first the background. We can see here this measurement. This is the background, and we know that has a background of around approximately very close to 0 particles in the air, and go during the process for increase the concentration to 6,000 concentration in mass. That means that this process has can evaluate, can assess with a high risk. Okay, during the measurement of concentration of nanomaterials, we can see here that this is the first detector, the detector that measures nanomaterials below 1 micra, from 10 nanometers to 1 micra, and and we can see here in this column is measurement the concentration in mass as well, and in number, sorry, and in the right axis is measured the parameter of the position in the lung, where because with this side of the nanomaterials, which is the concentration that could be deposited in the lung because for the size, no? And we see here that the concentrations step in this part is around the background, have no much risk, but there is a process that is correlated with the first peak here for the higher size, that it is really risky to do it. Okay, and yeah, and that is and here is also the correlation of the power transfer. Okay, the second part of the analysis, when we perform an exposure analysis, as I said before, is that is making the microscopy analysis. This analysis has to be done once later, when the first part is go to the industry, make the evaluation assessment, measurement the concentration for the different process, and the second step is we pick up the filters that has capped nanomaterials in the air, and we go to the microscope laboratory and perform this analysis. For example, I put here in the measurement of what are the particles we have measured in the process, in the later process. We have measured first the blank. The blank has normal materials, carbon and oxygen. And the different figures we can see it is, for example, here in the figure F, we see that is a fully crystalline material, a huge material that is composed for a lot of different nanomaterials. It's an aggregation of nanomaterials. That is a common process when we study aerosolization in the air for the nanomaterials, this aggregation of the nanomaterials. For example, if we study in attention which are the chemical analysis of these materials, we can see if we go to the column F, this one of here, we see that this materials is composed of carbon, oxygen, aluminium, and magnesium and silica. We can see, and also, for example, in the figure G, we can see that it is titanium in a 30%. There's a high concentration of titanium. One proposal that we can propose to this company is that they have nanomaterials and metals in the air, and then we recommend to all of the workers to have a protective equipment to protect for not inhalate these metals. Okay. Another scenario we have measured, for example, is similar to the later on. For example, here for the detector for nanomaterials, as we have measured here the different process, and we see that only in one process, when it is the cleaning with pressurized water, there is a high concentration, a very high risk concentration that we can evaluate as high risk. And the rest of the process increase a little bit, but not so. It's not so important. For example, for the same process in the materials that are higher than 1 micron for particles 1 micrometer, 2.5 micrometers, and 10 micrometers. This is the difference process that has been seen, and that is the detected peaks, and that is the difference material has been added during the process. Okay. Also, we have validate our device. First, the two examples that I explained before was in an industrial process where there is a very high concentration with a high production, and also we have made the other range in a laboratory. We have measured in the Nanoscience and Nanotechnology Institute in Barcelona, Spain, where they also have a manufactured nanomaterials, but the scale of production is very small compared with a production line in a fabric. In order to compare if the NanoExploreR device can be also competitive in a laboratory scale, as we have demonstrated that is competitive in an industrial scale production line. That is the different measurements we have performed. I will show you some examples only. For example, in this process, we have there was the synthesis of iron oxide of nanoparticles, and we have detected this rotovapor that perform the mixing of the different materials to perform the first step of the synthesis. The rotovapor was outside of the ventilation system, and we can see here also in the nanomaterials for the detector of nanomaterials how high is the concentration, how it is if we compare with the background, we can assume here that this is a very high risk to inhalate nanomaterials during the process of synthesis of these nanomaterials. And we also make recommendation to the user of this laboratory in order to put the rotovapor inside of with a local ventilation in order to extract this the high concentration of nanomaterials we have detected with our NanoExplore device. For example, with the higher particles, it's also important how increase the concentration of the level, but not as higher that has increased the nanoparticles concentration. When also we have capped nanomaterials with our filters, and you can see here the different pictures we have performed, and also the composition. Important is that we have detected iron. Iron, for example, in the picture D, this in nanomaterials. It's this particle, for example, is 300 nanometers and is composed principal for carbon, oxygen, aluminium, iron, hafnium. That means that it is important to improve the local ventilation in this lab, and also that every user that go inside of this lab has to wear a protective mask in order to avoid possible inhalation of nanomaterials and metals. Also, you can see here that in this materials is composed for a monoparticle that is a half a size of 100 nanometers. And also we can see a composition of different nanomaterials for 1 micra. And yeah, it is important that this and was very useful for making this implementation, because they improve these risk management measurements and improve this risk and disappear the risk we have detected. Okay. In order to finish my talk, the last slide, the last example that I want to explain to you is measurements we have performed in a train station in Valencia from the company of Adif. And this is a long-term measurements. The measurement that we have shown before is a short-term measurements. We have used the NanoExplore device only when the product has been performed during the process. That means that we have measurements no longer than 4 hours in continuous. This kind of measurements, the measurement I explained now, is a long-term measurements in order to implement this and to check if the NanoExplore device can also take care of measurements that has during days and weeks, in order to evaluate the environmental concentration of nanomaterials, not only in a different process. And as you can see here, these measurements will be performed from 29th November last year to the 13th of December, 2 or 3 weeks. And we can see here, for example, that I guess was a Monday. This one was a Monday, and this one was a Monday, a worker Monday. This station is surrounded for highways where there is a intense. This station is in the outside of Valencia, and the highways during the working days, there is a very high urban transit. And we can see here, we can detect here that is only in the part of the detection of of particles higher than 1 micrometer. We can see here the concentration of 1 micrometers, and then it's higher compared with the Sunday, for example. And this is a validation that our equipment also had validate and it's validated for a measurement short and long-term measurements. And for that, I will thank you your attention for this workshop. If you have a further question, please don't hesitate to put in contact with Carlos Fito and or Helene Prima from ENMs. Thank you very much for your attention.
Good morning to everyone. My name is Simeon Taskaris. I'm a GIS specialist developer, and on behalf of Geospatial-enabled technologies, I will present to you the functionalities of the NanoExplore web-based platform. A three-tier architectural approach was adopted. The presentation tiers is the front-end layer in the three-tier system and consists of the user interface. The user interface is a graphical one accessible through a web browser or web-based application, and which displays content and information to the end user. This tier is built on web technologies like React, JS, CSS, etc., and communicates with the rest of the layers through API calls. The application tier contains the functional business logic, which drive an application's core capabilities. PHP language lies here. The data tier comprises of the database storage system and data access layer. The PostgreSQL is used here in conjunction with InfluxDB for storing and querying raw data. The multi-tenant schema structure allows for addition of things and sensors with various characteristics and measured properties or custom types of places, thus ensuring the reusability of the platform. Time series of the observed values is indexed by timescale.db, a PostgreSQL extension to maintain high performance. Data is accessed by the application layer via API calls. The platform was implemented to support input data originating from the NanoExplore sensors. The platform provides both a publicly available interface as well as an administrative environment for registered users with advanced privileges. The operation of the platform is based on modern development techniques, open source technologies, and international standardization specification. An MPI is specifically developed for the NanoExplore project, supports the operation of the front-end part of the platform. The platform provides to end users with rich tools for data visualization and analysis and access to the raw data. The platform allows access to different modules. The UI approach is map-centric to allow users to locate data available at his area of interest. Main platform modules are map, real-time dashboard, data visualization model, statistical analysis module, sensor management module, alerting, user management module, and platform management module. This is the main system module available for public and registered user. In the module station are displayed on map. From the right menu, user can select a parameter. Then the map is refreshing, displaying only stations that are being monitoring the selected parameter. For each station, the last measurement, the last available measurement for the selected parameter appears as a label. From the bar at the bottom of the map, user can select a specific date range for fetching information. The date range filter is applied by clicking the show, the green button, and is reset by clicking the reset red button. By clicking a station in the map, a pop-up window appears, presenting data of last measurement and statistical data, mean, max, average, standard deviation, variance for the selected recording period. By clicking data analysis button, user navigate to data analysis module, in which data is presented for the specified combination, station, and parameter. The data analysis option is available for public data to non-signing and to non-signing users and also to the privileged users. Now the data analysis module. Data analysis is probably the most important system module. It provides access to visualization, statistical information, and analysis tool. Navigation data analysis tab assigned from the left menu and shortcuts can be done through the station modal window of map that analyzed previously. For previewing numerical statistical data, users select a station and a parameter. By clicking Show button, information cards with the following content are shown. Station and parameter information, map of the station location, last measurement and mean values for selected time of period, diagram with mean and max values, and also moving average diagram. User can access further analysis tools by selecting a date range at the bottom of the screen and clicking Show button. This way, the following information cards are displayed. Descriptive statistic, mean, max, mean, median, mode, STD, var, N, IQM, kurtosis, and percentiles. Histogram. User optional fields in mean, max values and bins. And click Show button to render the histogram. Also, there is a module for the linear regression correlation. Users select the second desired parameter and click Show button. Another module is the forecast. This module provides maps with forecasts for air quality parameters originating from the EU Copernicus program. First, the user select a parameter from the menu at the right of the map. Next, a layer about parameter forecast is displayed on the map. The data displayed came from a WMS service for the EU Copernicus program. Using the timeline bar at the bottom of the map, user can select a specific time for previewing the corresponding forecast map. Furthermore, user can click Play button for displaying a time animating map, which goes through all time steps and displays respectively information. Registered user can have access to additional features of the platform. For the authorized user, the platform user interface consists of a main navigation bar top of the screen. From the main navigation bar, the user can log out, navigate to profile, change language, and toggle side menus. A left side menu provides access to platform modules. And inside the main body actions, there are 4 shortcuts for the representing the main system module: map, data analysis, forecast, and alerts. By clicking the settings, a sub-menu that contains the following options appears. General provides fields for changing up metadata, type, descriptions, icon, appearance, header, footer, color, and parameters for map initialization, initial coordinates, and zoom level. Front page, from which for each local user can edit the context and formatting of the landing page text by using the integrated text editor. Furthermore, user can change the front page image. Policy, for each local The user can edit the content and formatting of the policy text by using the integrated text editor also. Email templates provides capabilities for email templates management. User can edit the context and formatting of each templates by using the integrated text editor. Things. These modules provides station management functionality, add, edit, delete. The operation is supported by a map control. By clicking a station on the map, the corresponding form is open for editing its attributes here. By clicking a data stream button inside the form, a pop-up appears for viewing information or change settings related to the parameters that are being monitored by the station. Using the selection menu at the top right corner of the modal window, user can select one of the following modes: info, that describes information about each parameter; edit, where user can delete parameter or edit its description. In addition, user can add a parameter by clicking the add button at the bottom of the modal here. And services, an API service can be implemented, provide information about measurements either in a JSON or a CSV format. User select the parameter that will be included into the service and click the add button. Then he fills in the required fields for service creation and click the submit button. For creating a new station, user click the new station button that is located in the toolbar at the top right corner of the map. Then a click on map should be performed for setting station location. Next, a form. No, sorry. Next, a form containing station attributes is open. User fills in required information and clicks submit button for station creation. From the same toolbar, user can set a new station location by clicking the Move Station button, and then drag the station icon to the desired position. To submit location change, user clicks Save button. In addition, user can delete a station by sequentially clicking the Move Station button, and then desired the station, clicking the desired station in the map, and click the Save button. The next is the sensors. A list of sensors is presenting along with the management tools. Using the search bar at the top, the user can execute a free text search for station. For each station, using the button at the left, he may proceed to edit or delete it. Furthermore, the user can add a new station by clicking the Add button of the button and fill in the required forms fields in the pop-up window. Parameters. A list of parameters is presenting along with management tools. Using the search button also on the top, at the top, a user can execute a free text search for parameters. For each parameter, using the button at the left, the user can proceed to delete or edit it. Furthermore, he can add a new parameter by clicking the Add button at the bottom and filling the required forms fields in the pop-up window. The user module, by selecting the tab user, a submenu that contains the following option appears: list and add. A list containing user information and the following management tools for each user: edit, view, drop, delete, and assign to group, role assignment here, an activation, the activation option. Add, if you click add here, the platform provides a form for adding a new user by filling in the following fields: username, first name, last name, role, email, address, and location. Raw data. This module provides access to raw data, data as they are initially uploaded to the platform. As a first action, user select a station from the right side menu and click a select button. Next, user can select specific parameters from the selection menu at the bottom right section of the screen. Then user can select the desired time period from the drop-down menu at the top right section and proceed to download the data in CSV format. Moreover, user can fetch data by submitting queries in SQL syntax or by using templates of pre-written queries. In addition, functionality is provided for creating graphical visualization for one or more parameters, with additional capabilities for selecting graph, visualization parameters, and more. Alerts. These modules allow the creation of alerts when a condition is met. For example, when a value of a parameter is over a threshold for a specific duration of time. For alert creation, the user selects a station from the form at the right side of the screen. By clicking select, a form is shown for filling the required fields that define the condition which trigger the alert. Specifically, a user fills in the following fields: parameter, threshold type, value below, value over, threshold value, minimum duration of a condition to be met in order for the alert to be triggered. Moreover, user can select sending emails periodically, filling the period in hours. Furthermore, can select sending an email when the alert stops. In the main section, a list is of alerts and their attributes is presented. For each alert, the user can delete it, edit it, or preview the corresponding station on map by using the three buttons on the left. The last module is the predicted environmental concentration. The predicted environmental concentration implements the proposed methodology of a multimedia modeling of engineering nanopractical with simple box for nano, model definition and environment of Johannes Meters, Albert Koolmans, Jan Hendricks, and Ding van Mint. The user must define the predicted environment concentration in air, in water, air, soil, sediment, the time, the density, the diameter, the particle Z potential, the overhammer constant for ENP water, the concentration balance, and the area. The result are two diagrams: nanometers mass for air, soil, water, and sediment per time, and nanomaterials area for air, soil, also for air, soil, water, and sediment per time. If you want to read the whole article, you can find it at this address. Thank you for your attention.